In this lecture, I am going to show you how the lock statement works in C#. You've already seen the statement appear a few times in the previous lecture, when I showed you how to lock several fragments of code to avoid a race condition. Let's start with the following code. I have two shared integer variables up here, both initialized to 1. Then there's the doWork method here that checks value2 and then divides value1 by value2 and then sets value2 to 0. By now, you should be alert to the possibility of a race condition in this code. If two or more threads call doWork, then it's perfectly possible for one thread to set value2 to 0, just as another thread is busy executing the console.writeLine method. The result? A division by 0 exception. To fix this code, I need to make the check and the division one atomic operation by adding a lock statement around these lines of code. So let me do that right now. Now the lock statement needs a synchronization object to work with. This can be any reference type. There are no restrictions. For now, I will simply add a private static class member of type object and use that for synchronization. There, that's it. The code is now guarded against a race condition. We say that the code is thread safe, meaning it can safely be called from multiple threads simultaneously without crashing. Locking a section of code is a very fast operation. On a typical modern CPU, the operation takes around 20 nanoseconds to complete. That's pretty fast. So there's no need to worry about the performance overhead of locking a section of code. The lock statement is what we call syntactic sugar. This means the C# compiler will actually expand the statement to a larger block of code. And lock is simply a convenience provided by the compiler, so we don't have to type all of that code every time. The code produced by the compiler is very simple, and you can easily type it by hand if you want. Here is the doWork2 method with the code of the previous example with the possible division by 0, but now with the expanded lock statement. As you can see, a lock is nothing more than a call to monitor.enter. The monitor class in C# provides for critical sections. The enter method enters a critical section and the exit method exits it. There's an extra Boolean variable here called lockTaken. This variable acts as a signal to the finally block down here. If the monitor was entered successfully, the Boolean will be set to true and the finally block will exit the critical section. But if for whatever reason the critical section could not be entered successfully, then the Boolean will be false and the finally block will do nothing. This setup with the Boolean field prevents a lock leak, where a critical section is entered but never exited, because the corresponding monitor.exit is not called. The advantage of typing monitor.enter and monitor.exit directly is that I can now use other features of the monitor class too. For example, there's a try-enter method that I can use instead. Try-enter expects a timeout as the second parameter, either in milliseconds or as a time span value, and it returns a boolean, true if the enter was successful, and false if it was not and the operation timed out. Providing a timeout is very important because you never know if the critical section will be released. If another thread is stuck in an infinite loop while holding the critical section, then your thread will wait indefinitely. A timeout will help you break out of this deadlock situation. You've seen that the lock statement requires a synchronization object. I created a special private object variable for that purpose. But you can also lock on any reference type you like, including the this value or perhaps even a type object. So you might be wondering if there are any best practices in choosing the synchronization object. And in fact, there are. You're advised to always use a private field as a synchronization object. The reason for this is simple. Consider for a moment that you lock on a public field. Now, because the field is public, another thread could also lock on that same field. Now, suddenly, you have an unexpected dependency between two threads that might lead to both threads blocking and waiting for each other. This can easily happen when you always lock on the this value. But when you lock on a unique private field that you create specifically for the occasion, then you prevent any other thread to lock on that same object. So now the unexpected dependency between threads can never happen. It's just another safety net to protect your code from unexpected results. Finally, let me show you another capability of the lock statement. Nested locks. You can arbitrarily nest locks inside each other like this. The thread gains access to the critical section when the outermost lock succeeds, and each subsequent lock is simply stacked on top of the first one. The critical section is released when all stacked locks have exited. In terms of the monitor class, this means you can have any number of monitor.enter statements, and the critical section is only unlocked when a matching number of monitor.exit statements have executed. Nesting locks is useful when you are calling a method from within a critical section. To demonstrate, here is the divide by zero code again, but this time I have put the actual division in another method. I can lock the original code in the doWork method, but then call into another method from inside the critical section and have that method also set up its own critical section. Both critical sections are stacked, so I can safely return from the innermost method while still retaining the lock. Only when I exit the outer critical section in the doWork method is the lock released. So in summary, don't worry about nesting locks, but just make sure you use the same synchronization object for each critical section. If you do, you can neatly stack the critical sections and the lock will not get released until you return from the first method. So, what have we learned? The lock statement in C# is syntactic sugar for a monitor.enter and monitor.exit pair, and it sets up a critical section. The monitor class also has a try-enter method that supports a lock timeout value. The lock statement requires a reference type synchronization object. You can use any object you like, but a unique private object field is recommended. You can nest lock statements. The critical section is unlocked only when you exit the outermost lock.